Hi students, this is the second part of the first chapter, relations and functions. In the first part of the video, we discussed about the definitions of relations and their types. Before starting exercise 1.1, we need to discuss one more definition, that is equivalence class. What is this equivalence class? Equivalence class is actually the subsets of the given set A. To understand this clearly, we need to understand this equivalence relation. So let's see an example for equivalence relation. From there, we'll derive the definition of equivalence class. Consider the example that a relation R is defined in Z, the set of integers. Given as R is equal to x comma y, where x and y belongs to Z, and the given condition is x minus y is a multiple of 3. Now we have to prove that this relation R is an equivalence relation. So in the first video we saw when a relation can be called as an equivalence relation. If the relation R is reflexive, symmetric and transitive, then this relation can be called as an equivalence relation. So first of all, we will prove this relation R is reflexive. So when a function is reflexive, if x comma x belongs to R for all x belonging to the given set Z, then we can say this relation is reflexive. So here x comma x belongs to R. Does it belong to R or not? X comma x means by the condition x minus x is a multiple of 3. X minus x is equal to 0 is a multiple of 3. Therefore, x comma x belongs to R for all x belonging to Z. We can say since x minus x is equal to 0 is a multiple of 3, x comma x belongs to R for all x belonging to Z. Therefore, R is reflexive. Now the second condition, symmetric. So how to check whether the given relation is symmetric or not? So here we have to consider an ordered pair, let x comma y belongs to R. So if x comma y belongs to R, then y comma x also should belong to R. In that case, we can say R is symmetric. So how can we prove that this relation R is symmetric? X comma y belongs to R. That means by definition, x minus y is a multiple of 3. Yes. Now we have to get y minus x is a multiple of 3. Because if y minus x is a multiple of 3, then y minus x will belong to R. Now what is that term which is going to relate this? X minus y is a multiple of 3 and y minus x is also a multiple of 3. Okay, it's just the negative of x minus y. If x minus y is a multiple of 3, then minus of x minus y is also a multiple of 3. For example, if 12 is a multiple of 3, then minus 12 is also a multiple of 3. So we can say if x minus y is a multiple of 3, then minus of x minus y is also a multiple of 3. And minus of x minus y means it is y minus x. If we remove the brackets, we can say it is y minus x. So y minus x is a multiple of 3. This proves that y comma x belongs to R. Therefore, R is symmetric. Now let's prove this relation R is transitive. This time we have to take two ordered pairs from R. So let x comma y and y comma z belongs to R, where x, y, z belongs to the set of integers, the given set Z. So this proves that by definition x minus y and y minus z, both of them are multiples of 3. If x comma y and y comma z belongs to R, then x minus y is a multiple of 3 and y minus z is also a multiple of 3. Now, what we are supposed to get here, just x minus z. Why we need to get x minus z? Because x comma z can belong to R to prove that this relation R is transitive. For that we should get x minus z is a multiple of 3. So what relation will make x minus z is a multiple of 3? is sum of this x minus y and y minus z. So will the sum of these two multiples of 3 will again be a multiple of 3? Yes. Sum of two numbers which are multiple of 3 again will be a multiple of 3. So adding two multiples of 3 is again a multiple of 3. Oh, x minus y plus y minus z will give us x minus z. So x minus z is a multiple of 3 and that gives x comma z belongs to R, proving that R is transitive. Now this relation R is reflexive, symmetric and transitive. Therefore it is an equivalence relation. Now let's see the definition of equivalence class. Considering the same example, here the given set is the set of integers z. So we know the z contains these elements. It's an infinite set. It contains infinite number of elements. So this is the given set. The equivalence class is actually the subsets of this given set Z. The equivalence class is the subset of the given set Z. But it needs to satisfy some conditions. So what are those conditions? We'll see with an example considering the same relation R. So here x minus y is a multiple of 3. Let's group the elements which are satisfying these conditions. That means we will find sum of the elements of this R. Sum of these elements of R. If suppose x is 1, if suppose x is 1, then what can be y? What can be y? So y can be, this x minus y should be a multiple of 3. So y can be 4. Or it can be 7. Or it can be 10. Because 1 minus 4, 3 is a multiple of 3. 1 minus 7, minus 6 is a multiple of 3. 1 minus 10, minus 9 is a multiple of 3. So, if one of the element is 1, then the other elements has to be 4, 7, 10 and so on. Now we can see these particular elements forms a subset of the given set Z. These 1, 4, 7, 10, etc. The next one will be 13, 16 and so on. What about the negative side? So this will be minus 2 because minus 2 minus 1 is minus 3. And here minus 5 and so on. So these elements which are actually the subset of the given set integers form a particular subset A. Let me call it as A1. Similarly, consider the x as 2. If x is 2, then what can be the values of y? So it can be 5, it can be 8. In the negative side, if you consider, then it can be 2. Shall we say it's minus 1? Yes, 2 minus minus 1 is 3. It's a multiple of 3 and so on. Now, if we consider the elements which are related to 2, it forms another subset of this given set Z. There is 2, 5, 8, then next one has to be 11 and go on and so on. And this side it should be minus 1, minus 4 and so on. So this is another subset of the given set Z. So what is the speciality of these sets? Now, if you take any two elements of this set A1, any two elements of this set A1 and form an ordered pair, then it belongs to R. If you take minus 5 and 4, yes, minus 5, minus 4, minus 9. If you consider 4 and minus 5, 4 comma minus 5, 4 minus minus 5, which is 9. It is also belonging to R. So, if you take any two elements of this set A1, then it forms an element of R, satisfying this condition. Similarly, if you take any two elements of A2, the subset A2, then they also will form an element of R, satisfying this condition, multiple of 3. In that case, what happens if we take an element from A1 and another element from A2. For example, let's consider minus 5 from A1 and minus 1 from A2. Minus 5 minus 1. Minus 5 minus minus 1, which is minus 4, not a multiple of 3. What happens if we take minus 1 minus minus 5? It's minus 1 minus minus 5 is equal to 4. Once again, not a multiple of 3. That means if you take any element from A1 and another element from A2, then this ordered pair does not belong to R. Or we can say any two elements of this set A1 are related to each other. Similarly, any two elements of A2 are related to each other. But any element of A1 is not related to any element of A2. Similarly, any element of A2 is not related to elements of A1. Such a subsets of the given set Z are called as the equivalence class. Now we can consider this equivalence class is all the numbers which are related to 1. So we can call this as equivalence class 1. This is actually the notation of the equivalence class. It can be called as equivalence class 1. Here A2 can be called as a equivalence class 2. That means all these elements are related to 2. Similarly, we can form one more equivalence class for this, all the elements which are related to 3. So this time we can find it directly that it contains elements that are multiples of 3, 6, 9, 12 and so on. And here it is 0, minus 3, minus 6 and so on. So here we can say it is equivalence class 3 or we can say it is equivalence class 0. Generally we use the smallest statement, equivalence class 0. Now let's see the definition of equivalence class. Let A1, A2, A3, etc. An are the n non-empty subsets of the given set A. Non-empty subsets of the given set A. So these subsets can be called as the equivalence class with respect to a relation R if it satisfies these conditions. The first condition is all the elements of A1 are related to each other. So that we can say all the elements of AI are related to each other. In second condition, any element of one set, let's say AI, any element of AI is not related to any element of AJ, another subset. So any element of AI is not related to another element of AJ. And the third condition, the union of all these subsets makes the given set A. The union of all these subsets makes the given set A. Such a subsets are called as the equivalence class. Now let's start exercise 1.1. Exercise 1.1 first question contains 5 parts. In all these 5 parts we have to check whether the given relations are reflexive, symmetric and transitive. Let's start with the first question, first part. Here the given relation R is equal to x comma y such that 3x minus y equal to 0 is defined in the set A, where set A is containing the elements 1 to 40. Here we have to show this relation R is reflexive or not. So being a finite number of elements, it's possible for us to identify all the elements of R. That means all the ordered pairs of R. We can see 3x minus y equal to 0. That means 3x is equal to 1. That gives y is equal to 3x. So it is possible for us to find the elements of R. So if you consider x is equal to 1, then y is equal to 3. If you consider x is equal to 2, then y is equal to 6. If you consider 3, then it is 9, and 4, it is 12. What happens if x is equal to 5? Then y is equal to 15, but 15 is not present in this given set A. Therefore, there are only 4 ordered pairs that belongs to this relation R. Now let's check whether this relation R is reflexive or not. So reflexive definition is A comma A should belong to R for all A belonging to A. Here if we consider one element just 1, even 1 comma 1 does not belongs to R. Here we have to understand one important thing that we have to recall from class 11. How we used to write the proof for some things which are true and false. If you want to prove something true, then we have to give a general proof. At the same time, if you have to prove something false, then for it, one example is enough. So that's what we can see here. 1 comma 1, just one example, does not belong to R. And this is enough to say that this relation R is not reflexive. If we have to prove it is reflexive, then we have to give a general proof. That we'll discuss in a different question. So here 1 comma 1 does not belong to R, and this simply says R is not reflexive. Is it symmetric? So what is the condition of symmetric? If A comma B belongs to R, then B comma A also should belong to R. Here 1 comma 3 belongs to R, but 3 comma 1 doesn't belong to R. Once again we are using a small example, and this says that R is not symmetric. Is it transitive? So how to check a relation is transitive or not? If A comma B and B comma C belongs to R, then A comma C should belong to R. So here we can say A comma B, that is 1 comma 3 belongs to R. So what is an element which is, what is the order pair which is starting with 3? It's having the first element 3, that is 3 comma 9. So 1 comma 3 and 3 comma 9 belongs to R. But 1 comma 9, does it belongs to R? No, it doesn't belongs to R. Therefore, this implies R is not transitive. So it's very easy to prove that a given relation R is neither reflexive nor symmetric nor transitive. Next question, first question, second part. Here the relation R is defined in N, the set of natural numbers, and R is defined as x comma y such that y is equal to x plus 5, and here there is a condition that x should be less than 4. So even though it is the set of all natural numbers, the infinite set, still we are given a condition x less than 4, so x can take the values only 1, 2 and 3. So we can see the relation R, once again it is going to be finite. So if x is equal to 1, then y is equal to 1 plus 5, that is 6. If x is equal to 2, then y is equal to 7. And if it is 3, then 8. So it cannot be 4 because x is less than 4. So only these three ordered pairs belongs to the relation R. So clearly we can see, just like the previous question, we can understand and write 1 comma 1 does not belongs to R, and says R is not reflexive. 1 comma 6 belongs to R, but 6 comma 1 does not belongs to R, and this says that R is not symmetric. Okay. What about the transitive? So that's an important thing that we have to understand from this question. Here we can see we are not getting any situation to prove whether this relation R is transitive or not. So what is mean by that situation? Here we have 1 comma 6 an ordered pair. There is no ordered pair which starts whose first element is 6. Similarly, here we have 2 comma 7. There is no ordered pair which is having the first element 7. So here we are not getting a situation that A comma B and B comma C belongs to R. Therefore, R is transitive. We conclude that R is transitive. If you have to prove it is not transitive, then you have to give a solid example. But it's not possible for us. So here we conclude that R is transitive. So how we write the explanation for this? There is no situation that A comma B and B comma C belongs to R. Therefore, R is transitive. So this relation R is neither reflexive nor symmetric but transitive.